Today we'll be going over the properties of quadratics that you'll need to know for the next videos in this series. But this is essentially a review on the topics, maybe the formulas that you need to know, or the properties of the quadratics that you need to know in order to understand polynomials and the roots of the polynomials better, which I'll go over in future videos. But this is meant to be a solid introduction to what you'll need to know. So we'll just go over quickly. What is a quadratic? Well, a quadratic is essentially a polynomial that has a degree of 2. And what we mean by this degree of 2 is that the largest x power in this polynomial is going to be the degree of the polynomial. So since the largest power in these x is 2, like this is 2, this is 1, and this has no x, the degree of the polynomial is 2. So those that describe quadratics, the set of polynomials that is of degree 2. And this is known as the standard form of the quadratic, which is called ax squared plus bx plus c. And a quadratic, just for a refresher, when you draw it on a graph, and this is the graph of when this is equal to f of x, where y equals f of x. So in that case, I'll have to describe this as the y-axis and x-axis. So a quadratic will often look something like this. So quadratic will look something like this. And there are many points on the quadratics that we like to observe. And one of those points is the vertex. One of those points is the vertex, and I'll mark it in this color over here. And this is known as the vertex. Vertex. And the vertex is very important because it is the maximum or minimum point in the parabola. So in this case, it's the minimum. So this is the minimum point of the parabola here. And there's only one point that touches at that minimum, and that is the vertex. Now remember, parabolas can also go the other way, like this way. So in that case, the vertex would be the maximum point. So I just like to point that out. In that case, the vertex will be the maximum point on this parabola. But besides the vertex, we also like to look at the roots of a parabola, and the roots of the parabola are where the parabola touches the x-axis on the coordinate plane, and we call those real roots. There are, of course, imaginary roots that you may have learned, and all of those roots, complex roots, but the real roots are where the parabola touches the x-axis. If the parabola doesn't touch the x-axis like this, then we say that the parabola has no real roots. So what else do we look at? Well, we also sometimes look at the y-intercept of the problem. That is known as the y-intercept. And same with this one. And other times we also look at how far the parabola has stretched this way or this way. So there's many properties of a parabola that we look at. But today I'll mainly like to go over the quadratic formula and how to derive it. So let me erase some of this stuff over here. Now usually you assign f of x in front of the thing, but just for the purposes of the video, usually you put f of x is equal to ax squared plus bx plus c. But let me go over how we would solve this problem. So what are we actually trying to find with the roots of the parabola? Well, the roots of the parabola are where the y equals 0. So we know that, and I'll write it in a standard form actually over here so that we remember what the standard form is. So we have f. So we have f of x is equal to ax squared plus bx plus c, where y equals f of x, and that'll be our graph here. So wherever the parabola, wherever these points are, is where the y value of those coordinates are 0. So since y is equal to this entire thing, we just set that y to 0, and we have to solve here. Now solving for x is not that easy over here. We can see that there's multiple, there's an x squared, and there's x, and there's not an easy way to distribute. Well, we'll use something called a perfect square trinomial. And the way we'll look at that is we'll look at this identity over here. And this is a very important factorization to remember. It's a plus b, the quantity squared, is equal to a squared plus 2ab plus b squared. And we'll see why that's useful in a moment. But for now, let's look at what we can do what we can do just for now. Now we want this x squared term all by itself for now. So what we'll often do is the way we'll do that is by taking the a out of all of these things. So if we take the a out, we'll have the x squared plus b over a. Remember, we took the a out of the bx. And we can also just leave the c out of that because, as we'll see, it'll be very useful to have the c on the outside. And we can set that all equal to 0. Now we can clearly subtract c on both sides. So what can we do from here? Well, one thing that we can do is notice that since there's a squared term in here, it would be interesting if we can write this like this, like a plus b squared, the quantity a plus b squared. So how can we do that? Well, if we take x as our a, we take x as a and some other value, let's say y, and we square that, let's see what we get. And that would be x squared. It's basically just the same as the above. X squared plus 2xy plus y squared. And I would really like to note here that this y that I used is not the same y as the y-axis. This is just a placeholder variable that I used so that we could see how this expansion works. So don't confuse this y with what I used for the original equation. So how can we use this? Well, we note that, but y is actually, remember, we have the x squared term is actually already there. So we're actually trying to go in the reverse direction. We're trying to go in this direction, not this direction. So it may look like, oh, we're trying to square this binomial, but no, we're actually going into the reverse direction. So in order to do this, how do we go from this direction to this direction? As you can see, there's only 3 terms on this side, but there's 2 terms here. So how do we get the extra third term that we need? Well, in order to do that, let's figure out what y actually is. So to figure out y, let's notice, okay, so if 2xy is equal to b over ax, then let's figure out what y is. So we can actually write that over here. So we know that 2xy is equal to b over ax. As we can see here, they're both the x terms in both of these equations. So if 2xy is equal to b over ax, then what is y? Well, the x and the x will cancel out on both sides. I'll make that clear. It's not very clear there, but the x and the x cancel out there. And if we divide by 2 on both sides, what we'll get is that y is actually equal to b over 2a. And this is useful because now we know exactly what we have to add to this to get a perfect square trinomial. And once again, keep in mind that this y is not the same y as the y-axis. Again, the y-axis, the y that I used in the original equation is actually equal to 0 because the y value of the coordinates of the roots is equal to 0. So this y is just a placeholder variable. And so let's quickly do that. Let's do a times, it's not exactly the same color, but x squared plus b over ax, and then we'll have, we know that y is b over 2a, and we want a y squared term, so in order to do that, we just do b over 2a, the quantity of b over 2a squared, and that'll be b squared over 4a squared. Now we can't just go adding terms randomly, so we have to actually do something. We have to actually add the same result on the other side in order to keep the equality that we have. The way we'll do that is we realize, okay, we took out the a from this b squared over 4a squared. So what this actually is when we bring it to the other side, is b squared over 4a. Because when you multiply the a through, this term is actually b squared over 4a squared. So over b squared, this term becomes b squared over 4a. So we still have our minus c over there, and let's see what we can do afterward. Well, we have this perfect square trinomial, so let's simplify that. And this is important here. We have x plus, and we know that y is actually just b over 2a. So x plus b over 2a, quantity squared, and that times this a that we have over here. That is equal to b squared over 4a minus c. The next best step seems just to divide a on both sides. So let's do that by dividing by a. And what will we be left with? So x plus b over 2a, quantity squared, and that is equal to, now we see that this a and this a cancel out, so what we're left with on this side is b squared over 4a squared. This a divides one more time, and this becomes simply c over a. Now we would like this to be in the common terms, so the way we actually do that is multiply 4a and 4a on both sides. So I'll actually write that. So what we're doing is, to make this in the common denominator, we multiply 4a here, and we multiply 4a here. Notice that since we're multiplying by 4a over 4a to this term, it actually just cancels out and becomes c over a, so our quantity is not changed. So now this is equal to b squared minus 4ac over 4a squared. Now this is useful because when we take the square root of both sides, what we're left with is, take the square root of both sides, what we're left with is this 4a squared actually becomes, 4a squared actually becomes 2a, because the 4 is a perfect square and the a squared is a perfect square. This becomes 2a over, and then this becomes the square root of b squared minus 4ac. And this becomes, since the square root and the square cancel out, we simply get, almost there, x plus b over 2a is equal to that. Let me scroll down a little. Now we're almost done here, and we have x is equal to, now we subtract b over 2a on both sides. But what we do have to remember is that when we take a square root on both sides, we actually have to have a plus or minus there, because negative 2 squared and 2 squared are both equal to 4. So it's always important to remember that plus or minus symbol there. So let's subtract b over 2a on both sides, and we get negative b over 2a plus or minus the square root of b squared minus 4ac over 2a, and this is more popularly written as, so we have negative b plus or minus the square root of b squared minus 4ac, and all over 2a. And this is equal to x when this whole expression is equal to 0. So that's very interesting. This is the formula for negative b plus or minus the square root of b squared minus 4ac over 2a, and this is a formula for finding the x value for the coordinates of these roots over here. So since the roots of a polynomial are very important, that's why we're looking at this formula. So what else can we look at instead of just the formula? Well, we can also look at factoring. So here's the second, one of the most important things besides finding the roots of our parabola, and this actually helps you find the roots of a parabola in cases where you don't want to use this relatively lengthy formula. So one way you can do this is we can actually think about an actual example just to make things easier, and the example that I'd like to use is 2x squared minus 13x plus 15. So the way we factor this, and as you see in the next video, there's a reason why we factor it this way. But the way we factor this is that because what we do is that we find a value where the first coefficient, and the constant term, we multiply those two together. So when we do 2 times 15, of course, we get this is equal to 30. Now 2 times 15 is equal to 30. So what we do is then find a way to split up the center term. So we'll do that, this blue over here. So we find a way to split up that center term such that that split up multiplies to 30. I feel like an example would maybe help more with the understanding of this. So let's try to see why. So let's try to find something that splits up in such a way. So since we want a way to split up the value of 13 such that it equals 30, the multiplication of those two values, we often write that as we need two numbers a and b such that a plus b is equal to negative 13, and we need it such that ab is equal to 30. And this comes a lot with practice. There is more guaranteed ways to do this, but at that point, you might as well just use the quadratic formula. But this is very good for quadratics that you can do much more simply. So this comes with intuition, but when I see like negative 13 and 30, I immediately think of 10 and 3. And since a and b can be negative 10, let's say, negative 10 and negative 3, we know that negative 10 plus negative 3 is negative 13, and negative 10 times negative 3 is 30. So that will indeed be the correct, the one we're looking for. So let's write that in here. So what we do is now we split this up into 2, and it's very interesting why it doesn't matter which direction you split it up. You could have put negative 3x and 10x on this side, or negative 3x minus 10x. It doesn't matter which order, but eventually you'll come to the same factorization. So now what we do is we group these two parts. into 1 and factor the common parts of it. So we see that 2x is factorable out of both of these, so we take out the 2x, and we see that in order to get that left over, we have to multiply by x, and then here we have to multiply x minus 5. So let's do that. And we do the same thing here. We take out the coefficient on this side, so that becomes negative 3 times x minus 5. And now, using the distributive property, we notice that, okay, well, look, this term is the same as this term. So that what we can do is we can actually undistribute this into a different way. Undistribute this in a different way, and that'll be 2x minus 3. 2x minus 3 times x minus 5. 2x minus 3 times x minus 5. And we've actually factored our original quadratic in a way such that we can find the roots easily, because now if we set this equal to 0, for example, we can realize that the roots of this quadratic were actually just where either of these quantities is equal to 0. Now, how can we do that? Well, we simply set each of them equal to 0. So we have x minus 5 is equal to 0, and we have 2x minus 3 is equal to 0. So from this one, we get x is equal to 5. From this one, we get x is equal to, x is equal to 3 halves. So now we can also just substitute this in to see if it works. So let's see. 2 times 25 is 50, minus 65 is negative 15, plus 15 is indeed equal to 0, so this is a correct solution. And we plug in 3 halves. 2 times 9 over 4 minus 39 over 2 plus 15, and if we simplify this, we realize that 2 times 9 over 4 is just 9 over 2, minus 39 over 2 is negative 30 over 2, plus 15, which is indeed equal to 0. So this is also a correct solution. So we can see how in this video we've learned two powerful techniques in quadratics that allow us to find the roots. And those two powerful techniques are the quadratic formula, which we saw over here, and we also know that factoring can help us whenever we want. Now, this is a very comprehensive review, and if you didn't understand anything in this video, I highly recommend to you to experiment on your own, see what you can figure out about quadratics, and we feel that experimentation is one of the best ways to learn. So oftentimes, if you're kind of struggling with something, just try different things out and try to find interesting things. So I hope you enjoyed this video. This was essentially just a review, and for next videos, we'll use these concepts and see why factoring works, and an even more interesting study of higher degree polynomials.